Welcome back everyone to the guest lecture 2 of Machine Learning 1 course. Yeah, so today we have with us Devanshu Arya. He will be speaking on graph neural networks. And before we give the floor to Devanshu, let me introduce him. So he is currently a PhD student and he is a PhD candidate in the Intelligent Sensory Information Systems group at the University of Amsterdam. And he's also a data scientist at Store Shippers, a company based in Netherlands, in Amsterdam, Netherlands. And his current research focus is on representation learning on graph structured data, in particularly multimodal learning using hypergraphs. He has been working towards developing graph-based deep learning models that are scalable to datasets with many modalities, with applications in recommender systems, link predictions, and neuroimaging. So he has also worked with our last guest speaker, Dr. Raj Thomas as well. He is part of the Asgard project, whose aim is to develop AI-powered solutions for forensic investigations that can directly contribute towards law enforcement agencies' technological autonomy across Europe. He graduated from IIT Kanpur in 2015 with a BTech and MTech dual degree in electrical engineering. His formal background is in speech signal processing, and he has worked on developing voice activity detection algorithms during his master thesis together with NTNU in Singapore. The topic that he's going to speak on is graph neural networks. This is quite a hot topic in the field of deep learning. I know many of you are still starters in deep learning, so he will be keeping his presentation quite simple so that everybody can get on board. And just to add on, he is also a part of the Transmute AI lab. He's an active senior researcher in the lab. And if you're interested in future to work as part of the lab, then this lecture might be right. Yeah, so that's all about him. Now let's hear directly from him. So, Devanshu, can you share your screen?
Yes, thank you, Deepak, for the introduction.
I'll stop. Side.
Yes. Can you see my screen?
Yeah, we can see it.
Okay. Okay. So thanks for the introduction and for inviting me to give a talk in your course. So I'll directly start with the slides. And if you have any questions, we can like take it after the talk, or even you can mail me anytime, anyone, if they have any kind of questions regarding graph neural networks. I'll keep it very high level, as in I won't get to the very details about graph neural networks, but I'll just give you the brief introduction of what is graph neural networks and why it has come to origin. So the first of all, this is a very brief outline that I have prepared for this talk, where I'll first talk about why graphs are important and why is it different from images, videos, and text. Then in the second part, I'll talk about the basics of graph neural networks, like what is the input, what's the output, what kind of loss functions are created in this domain. And then I'll talk about the most common tasks and architectures which have been around in the past 3-4 years. And finally, just a basic overview of applications that has been going around these days. So first of all, I'll tell a brief history about graph neural networks. It's a very recent topic. So it's been hardly 4 years for the topic to originate. So the main motivation for like creating a whole neural network setup on graphs is basically because the representation of data is very different in graphs versus in grids. And when I talk about grids, I talk about these kind of data, which are images, speech data, text data in NLP, or videos. So one thing that is common in all these kind of data sets are that they are grid-based data sets. What I mean by grid data is, let's say for images can be represented on a 2D grid. Uh, Basically, you can represent an image as a matrix where each pixel is a point, and then the next pixel can be defined spatially. That is, if there is a, you can basically in an image you can say that the left eye of a person will be from at the left position from the right eye of the person. So there's a spatial coordinates, and it can be represented on a 2D grid, which is a commonly it's a mathematically it's a Euclidean domain. Similarly with speech, you have a 1D grid, and and in this grid you can basically, from left to right, you can basically traverse, and the traversal will be temporal. So what I'm saying right now versus what I'm saying, what I'll say 5 minutes later, will be temporarily connected, and you can represent it via a point on a grid. And videos can be represented on a 3D grid, where on the XY axis are the pixels, the X pixel, Y pixel, and the Z axis is basically the temporal connections. So all these kind of data sets have a very regular spatial structure, which I was talking about. So one part of the data, or one part of the image, will be spatially connected to the other part of the image, and you can basically refer it something like, okay, this a cow is on the left side of the building, something like this. So this is what we traditionally, all the convolutional neural networks and all the deep learning methodology have been surrounded over this kind of data sets. So how convolution works on grid data is simple. You have a template, and you traverse that template or the filter over this grid data, which is the core base of convolution neural networks. So what happens in like, especially in 2D grids, is you have a pixel, which is let's say the ith pixel, and you have a jth pixel. So you can pass information from the ith pixel to the jth pixel, and this passing of information can be structured spatially. That is, you can say that for the jth pixel, the messages will be passed from, or the information will be passed from the rightmost, top rightmost, bottom rightmost, and the uppermost and the lowermost pixels. So all nodes of this template or the filter are always ordered or positioned in the same way wherever it is. So that is why the convolution on grids are translational equivariant. This is the most common convolutional example in images, where basically you have a filter and you traverse it through an image to get a hidden representation of the image. So this is how convolution has been defined traditionally on grids. So this is just to give a brief prelude to the core concept behind convolution on grids, and then we'll talk about how and why graphs differ from this kind of theory of convolution, and why is there need to define a new setup for graphs. So all these data sets that we are talking about have these spatial relations, and they can be represented on a grid. But what if we come across data sets which are something like these? So let's say you have a route mapping, or a traffic network, or a social network, or brain connectivity, protein-protein interaction network, these kind of networks. Here, there is no notion of left, right, topmost, uppermost, rightmost, nothing, because it's just, so they are just nodes which are spatially independently placed, and they have relations between them. In such kind of data sets, uh, they cannot lie on a grid. You cannot position them on a grid, and that grid won't be uh, a unique grid. So basically, you can position each node of these network wherever on the. So one node can be on the left part of the other node, or on the right part of the other node, but the semantic meaning will be the same. So these all kind of networks are can be defined on graphs. I hope everyone knows the very basics of graphs. So a graph is a data structure which has two components, vertices and edges. A graph can be described by these two components: the set of vertices and its set of edges. These edges can either be directed or undirected, depending on if there exist directional dependencies between vertices. To keep it simple, in the entire talk, we'll talk about undirected edges. So that is there is no directional relation between one node to the other. These vertices are often called nodes, so that I'll be interchangeably using these terms: nodes, vertices, edges. And mathematically, a graph is represented using an adjacency matrix. What an adjacency matrix is basically, if you have a graph with 5 nodes, then an adjacency matrix will be a 5x5 matrix, where it will where it will basically provide you the information of which node is connected to which node. So if a ith node is connected with jth node, then in the matrix, the ith row and corresponding to ith row and jth column, there will be a 1. Otherwise, it will be a 0. And this adjacency matrix will be a diagonal matrix. So this was the whole basic concepts of graphs, and why we need graph in day-to-day life other than the usual grid-based data structures. So a graph data structure is completely different from a grid-based data structure. I hope I have made it clear that there is a very strong need to come up with methods and architectures which can be worked around with graphs, because in grids you cannot perform such things. For example, let's say if you want to perform convolution on graphs, so in this example you can see that this node J3 has no specific position. Even if I rotate the graph is the same. It has the same meaning. Everything is same. But you cannot say that J1 is to the left of J3, because J1 can be very much on top of J3, and there is no spatial relation between J3 and J1. So there is no node ordering. So if there is no node ordering, then how can we match template features with data features when there is no relative position for data points? So something like this. How can we do such kind of operation where we can traverse the filter over the data points? The second thing is the correspondence of nodes is lost on graphs. There is no up, down, right, left in graphs. So to tackle all these issues, we basically have to come up with a new set of theory and architecture to define convolutions, because grid-based CNN architectures cannot be applied on these kind of data. So the research world realized it, and then they came up with something called as graph neural networks. So the whole concept behind graph neural networks is to perform learning on graphs. But before that, I'll just give you a brief introduction of what a graph means and what is the input to these graphs. So a graph is accompanied by nodes and edges. Generally, each node will have certain features, which is basically a vector of some numbers. These features will be defined by the might not have features in them. Again, these features will be accompanied by a vector. So you can imagine this something like, so if this graph is a social network, and each node of this graph is basically a person, a user, and the connection between one user to the other is the friendship connection. So then the feature of each of these users can be the kind of images they post, the time when they are active on the social network, or even the text that they write. Everything, you can just put everything as a feature for that node, which is the feature for the users. And the third thing is the adjacency matrix, which I talked about, which basically gives you the relations, that is which node is connected to which node in this graph. So all the methodology that will be defined over the course of graph neural networks will have only these three components: node features, edge features, adjacency matrix. Node features or edge features is basically optional. You can very much have a featureless graph as well, but you need adjacency matrices. So some of the challenges that are solved using graph neural networks are node classification, link prediction, community detection. I'll go through one by one for each of them. So in node classification, basically what happens is, as you can see from the figure, let's say there are 9 nodes, out of which 2 of them are blue node, 2 of them are orange nodes. So they are labeled nodes. I'll get back to the social network example. So let's say you have 2 kinds of people. One is one who doesn't like sport, and one who likes sport, right? And you have this friendship network, like you know which user is friend of which user, and you, out of 9 of them, you for sure know for 4 of them that 2 of them like sports and 2 of them don't like sports. And you'll come up with the question is, come up with an algorithm or a network or something that will eventually classify all the other nodes, that will classify all the other 7 nodes into people who like sports versus people who doesn't like sports. The second problem, which is the link prediction problem, is basically predicting that, okay, it's also called recommendation of saying, so it's basically predicting that one node can be connected to the other node. That is, in terms of social network again, that one user can is very much likely to become friend with the other user. So you can predict or give recommendation to that user, saying that, hey, you can send a friend request to that user because you have similar background, same school, same college, or same company, or whatever. So that is link prediction. Another kind of problem is on community detection. So let's say you have been given this huge graph of people, or let's say again users in social networks, and you want to basically cluster these users based on something which is like um, their uh, their background, or their or let's say to what kind of institute they have been to, what kind of colleges they have been to. So you can cluster them, that okay, these people have gone to engineering colleges, these people have gone to has done something with economics and all this. So this is kind of a clustering which is performed in graphs. So these are completely new challenges or new tasks, which is very much similar to image classification, or clustering in images, or recommendation in images, but in a completely new setup, where instead of using a grid-based data, we want to use a graph-based data. The history for defining convolution or any kind of learning in graphs actually goes back to 2005, but it was only after 2016, especially after 2017, I'll say, that things have kicked up. And after 2018, there has been a big explosion of graph-based architectures and learning algorithms. Now it's very hard to keep track of all the architectures actually. Uh, I'll emphasize on one thing here, that is all these graph-based methods um, can be classified into 2 parts: spectral method and spatial method, that I'm showing here. For this lecture, I will only focus on spatial methods. Spectral methods were quite popular before, like in 2000, before 2017. But after 2017, the spatial methods have kind of kicked up. And there are several reasons for it. I won't get very detailed into it, but I'll just give a brief summary that spectral methods are more uh, computationally expensive, and also hard to infer, hard to basically do any kind of uh, reasoning over these methods. So for the sake of time and this lecture, I'll just focus on the spatial methods. So the spatial methods is basically also referred to as message passing neural networks. So the basic concept or the aim of spatial method is to generate node embeddings or learn node embeddings based on information from local neighborhoods. So for example, in this image, uh, if you want to, so basically the red node, so initially you'll have all these features for all these nodes. But what we want is basically for the, we want to learn something about this red node based on the information that its neighbors have, so that eventually we can make some kind of inference about this red node. So it will have its own feature, but what we want is to enhance its own feature with its neighborhood. So coming back to the social network example, let's say uh, we for sure know that out of its four neighbors, two of them watches sports. The red node, we have no idea if he watches sport or not, or doesn't watch sport. But can we gather information from its friends and come up with some intuition that okay, red node has a probability of watching sport which is higher than 80%, and it's truly based on its own information plus the information from its neighbors. Maybe it's their neighbor posted something about sports, and at the same time he commented on their post. Anything of any kind of features that can help in deciding such information for the red node. So basically, in this special method, what we want to do is we want to aggregate information from the neighbors using a neural network architecture. So there are basically two things that is happening here. First thing is we want to aggregate information from the neighborhood for this red node, and the second thing is whatever information that we have gathered from the neighborhood, let's call it A. We want to combine that information with the red node's own information, so that they combine it in a way that we can make any kind of inference for the red node. So for that, we basically need two functions. One is the aggregation, that is how are we going to aggregate from the neighbors. Second is combination, that how are we going to combine the feature of the red node with the feature of the neighborhoods that we have aggregated. Uh, I'll just pause for like 10 seconds so that everyone can like see this thing, what's happening. So I'll reiterate. It's all about fetching information from the neighbors and combining that information with your own information to get any kind of uh, result or inference. I hope everyone gets this concept. It's a very basic concept of neighborhood information propagation. So this is like the core concept of any spatial graph neural network, and how are we going to design a neural network on top of it, do any kind of weighted learning, or all these things will be uh, I'll talk about it later on, but that's the whole core concept, the basic. So this whole message passing or the neighborhood aggregation in a neural network happens recursively. So for example, that I'll show you like I have given some names to them. So for example, you want to know more about the node A. You want to gather information for node A from its neighbors. So then you'll basically transfer information from node B, C, and D. But again, for node to get information for node B, you'll gather information from node A and C. For C, you'll gather information from its neighbors, which are F, E, B, and A. And for D, you'll gather information from A. So basically, in order to get any information for A, you'll go 2 steps or 3 steps behind. So this happens recursively. So basically, what we are doing is for all these nodes, let's say the yellow, green, red node. So this is a two-layered message passing. So let's say for this green node, you will first pass information from its one hop neighborhood, one hop as in the nearest neighborhood, and then that nearest neighborhood in turn will be getting information from their neighborhood, which is all the other neighborhoods. These squares that I'm talking about here, that is shown here, I'll talk about it later. It's basically the aggregation that I was talking about. So if you can see these dark squares on the bottom, so these are the aggregations from the neighborhood. And finally, when these gray squares are the combinations from all the neighborhoods to the specific node. So this is how the entire message passing architecture looks like in a graph neural network. So each node passes information to the other based on their connections. So there are two basic things in order to like train a model or define any kind of functions for passing information to A. You just don't want to pass random information to A, which will be noisy. So you want to pass, let's say, from B to A, the information that you want to pass is very less compared to C to A. So you have to learn these weights, like how much information you want to pass, what kind of features are important that will determine whether A likes sport or doesn't like sports, something like this. So for this, you need to define a neighborhood aggregation function. And then the most important part is you need to define a loss function. This loss function will be basically, you'll calculate this the gradient descent on this loss function, and then will be back propagated to adjust the weights of these aggregation function, which I'll talk about later. But this is how it will look like. So what we want is uh, we want to quantify the message or the information that A will receive from B, C, or D. It won't be equal, because if it is equal, then there will be noisy information. So, so for A to receive any message, it will, so let's say the message or the features that A has is called HV. V is the node A. So it will have features of its own, features of its edges, the neighborhood aggregated feature, and the neighborhood state at that hidden layer, uh, which is kind of a neural network architecture. So basically, uh, you are passing it recursively. So at each state, this edge will be changing. And this O function, the G function here is the combination function that I was talking about here. So the aggregation function is basically function F, and the combination function is function G. So what we basically want to find out are the functions F and G, and this will be calculated based on back propagation and back propagation. So and that will be very task dependent. So we have to coin a loss function, and then based on that you can back propagate. So it's all about, so the whole concept is behind this message passing and getting information from the neighborhoods. So how do we choose these functions? The aggregation function and the combination function. I won't talk a lot about these things, but very simply put, let's say in the initial layer of a neural network, which is the 0th layer, the feature vector of a node is xv. Then in the kth layer, like after k layers of neural networks, uh, the whole message that will be passed to it will be basically an average of all its neighborhood multiplied with some weight function, which is wk, and the previous layer embedding of v. So basically from this image you can see, uh, so these gray squares are the layers of the neural network. So the second layer of the neural network will get a message from the previous layer. So the last layer that you can see here, I don't know if there is an arrow mark which I can just point out. And so this is the entire function that is required for training any graph neural network. It looks a bit complicated, but the thing is, I'll show you later on that it's just an extension to multi-layer perceptron. So in summary, these are the 5 things that we need to know to train or to understand any graph neural networks. The first is the message. Each node has some message or features. Second is the aggregation. You need to aggregate in the message or the features from neighborhood nodes. Third is the layer connectivity, which is basically how do you connect from one layer to the other, a function or uh, um, an activation function. Fourth is the graph manipulation. By graph manipulation, it is basically data pre-processing. That once you get the features, do you normalize the feature and all this thing? That's graph manipulation. And the fifth is the learning objective, which will be the loss function, so that we can train the entire network. So this is how a graph neural network looks like, or in a nutshell, this is how it is. So you have, and this is just a 2-layer network. Most of the time, graph neural networks are not very deep; they are only 2-layered network. The most common or the most famous graph neural network architecture is graph convolution network, which was defined, which was coined in 2017 by Thomas Kiff and Max Welling from University of Amsterdam. So what it does is basically so the whole concept here is, if you consider this red node here again, so the information that will be passed to this red node from the neighborhood will be basically the mean of the features of the neighborhood. So the aggregation function is just a mean, and the combination is just summation. So basically what you do is, I'll come back to the example here. So so all these 4 neighbors of this red node, you take those the features of all these 4 nodes and take a average or a mean of these features, and then just add it to the nodes feature, the red nodes feature, with certain weight function. So the idea behind such such an architecture is basically, you want to say that whatever the neighborhoods features are, you can give a weighted mean or just an average mean, and then pass it to the target node and do any kind of inference. And you can either do a weighted mean or just a normal average mean. This was the most, so this is called vanilla GCN as well, because this was the first time any such kind of architecture came into existence. So it has a very linear complexity. The main thing that I wanted to focus on was this thing in the red bracket. So if you closely look at this formula, so H is the feature matrix of this graph. So this feature matrix will be number of nodes cross the dimension of the features, and W is the weights which you want to learn. If you forget about A right now, just leave that A aside. Then H times W multiplied with non-linearity or sigma is basically multi-layer perceptron. It's nothing more than that. So when you multiply an adjacency matrix or A, you basically want to say that, okay, so this A actually adds up the information and then multiplies with the weight matrices. Whereas in multi-layer perceptron, each data point is associated with one weighted vector. So in summary, this graph convolution network is just an add-on to the multi-layer perceptron with adjacency matrices, so that you can combine or average out the features from the neighborhoods. So this is the concept or the whole theory behind graph neural networks, especially graph convolution networks. But how to train such a network and why training such a network is important and what kind of tasks we can do is is something that is of more interest that I'll talk about. So the first task that is performed in graphs is a semi-supervised node classification, which I was talking about earlier as well. That you have uh, you have a graph where some of the nodes are unlabeled and some of the nodes are labeled. So, for example, in this one, the black circles are labeled and all others are non-labeled. And the task is to predict node label of unlabeled nodes. And the input basically is the feature matrix. So where n is the number of nodes, e is the feature dimension, like the number of dimension of features for each node. And a is the adjacency matrix. So adjacency matrix gives you the information of about which node is connected to which node. Very simple, and this is the problem statement that is most common. For simplicity, we assume that features on the edges are not present, and each edge is undirected with just with no weights. That is, it's a uniform weighted graph. So how we do here this whole semi-supervised node classification is you have an input graph. You perform message passing on each of these nodes. So the first hidden layer that you see, all these purple nodes are the purple nodes are the one where you are passing message to. So you'll do it for all the nodes in one hidden layer, and then you'll combine these features and then perform a non-linearity. Then again do the same thing, non-linearity, and then you'll combine. Once you combine, then the features for each node is basically we will have information from the features of their neighborhood nodes, and then you apply a softmax on each of these nodes to perform classification. The loss function for such a thing you can, so in this paper the loss function was a log loss, but you can coin it in any like any binary loss as well. But the whole concept behind semi-supervised node classification uh, is to perform message passing, and in the end, once you get the output, which is Z, then on top of Z, you can just train a multi-layer perceptron. That's it. Uh, Using this kind of an architecture, you can do all kinds of node classifications in social networks, in citation networks and all. The second kind of task that is very popular, especially these days, is graph classification. So in graph classification, instead of a single graph, you have like 1,000 graphs or 100 graphs, and each graph has their own meaning, and you want to classify those graphs. What I basically mean here is there will be certain connections in a graph which sets them apart from other graphs. For example, in the left one, uh, let's say you have molecule graph. So you know that this kind of architecture is toxic and this kind of architecture is non-toxic. And then you have been given two random graphs and you have to predict whether molecules are toxic given the set of known examples. So you will be given a set of graphs with feature matrices and the adjacency matrix associated with each one of them. Some graphs are labeled, some graphs are non-labeled, and you have to basically predict labels of unlabeled graphs. Again, for simplicity, I'll get you back to the same architecture where you will do message passing on each of these graphs separately, and then combine and for each and once you do message passing, then for each graph what you'll do is either sum up the features of all its nodes or concatenate all the features of the nodes and perform a classification. So basically what you'll do is, let's say you have n nodes, Then at the end of this message passing, you will sum up all the features of all these end nodes and then uh, apply a softmax function. And you will do it for all the 100 graphs and train a neural network. So this is the second kind of second kind of task that is performed in graph neural networks using graph neural networks. The third one is link prediction, which I talked about earlier. So again, in this task, what happens is you get an incomplete graph as an input, again with feature matrix and adjacency matrix, with some pre-processing, which I'm not talking about. You can do your own homework with the pre-processing part. Uh, and the given things are the links which are present and most are absent. So the task is to predict links between nodes. Uh, Again, we can use the same architecture for this thing as well, where you do message passing for everything. Especially, I'm oversimplifying it, but you can do this message passing, come up with the final graph, and then do some kind of association or classification on top of the learned node embeddings of features. So this was all about a very basic brief overview of all the three tasks, and I have used the same architecture to show you how just by doing message passing or this kind of two hidden layer architecture, we can come up with node embeddings. And once we have those node embeddings, uh, we can learn any task, and then you can do back propagation and all. So yeah. So one thing that is noticeable is whatever we do, the graphs are fixed. That is, all the nodes are present during training time. There is nothing, no concept as what if a new node comes into the graph? Where will you fit that node? So this is a concept that is gaining more and more uh, interest, and I just wanted to talk briefly about it. So which is called transductive versus inductive learning on graphs. Again, very simply put, in transductive learning, we assume that all the nodes are part of the graph before training. So whatever you do, um, all the nodes are there in the graph. Some are labeled, some are non-labeled, but they are always a part of the graph. You cannot do inference on a new node, which was not part of the graph during training. So transductive learning builds a model that fits the training and testing data points it has already observed. Just a brief overview of what I said about transductive learning. So you have these 6 nodes, and you want to do some prediction on these nodes. Maybe say node classification, link prediction, or whatever. All the three tasks that I talked about. But the the concept is that all these 6 nodes have to be present during the training set, so that you can perform message passing on these 6 nodes, and then in the end you can do inference. So the test set is part of the is present during the training itself, which is a very new concept, which is not what we have usually during in image based or video based deep learning methods. So yeah, I just want to absorb what I said. So basically, all these nodes, all these 6 nodes, uh, let's say you know three labels of 3 nodes, you don't know the label of 3 nodes, but um, you'll perform message passing from all these 6 nodes. It won't be like, oh, these 3 nodes are in the test set, so I won't do message passing from these 3 nodes. So this is what we call as transductive learning, and this was being done till 2018. I'll say so. All the methods that has been coined up till now has been on transductive learning. So then people thought about what if a new node comes in, or what if someone, let's say in the social network example, what if someone new joins Facebook today? How will you classify it? Where will you put it in the? Where will that guy be put in the graph? And do we have to retrain the model, just because a new person joined the graph, or just because a new node has been introduced in the graph. So then came the inductive learning. So inductive learning tries to build a generic model where any new data point would be predicted based on an observed set of training data points. So it can predict any point in the space of points beyond the unlabeled points. So basically what it does is it trains on one graph, which is on the left side, and it can generalize or give predictions on the other set of graph, which might not be part of the training graph itself. So this is so whenever you read a graph neural network paper or a blog or something, this will be something that is always present, whether this method is transductive or inductive. Inductive methods are more advanced, but at the same time, it involves more computations. Computations during training, not during testing. During testing, it's more efficient. I hope I was clear till now. I'll just very briefly explain some of the most common graph neural network variants. I won't get very deep into the architecture, but these are the architectures which have been uh, quite famous. One of them is Graph Sage, which again came in 2017. Uh, this architecture was the first one to introduce inductive learning on graphs. And how it does is it does not use the entire adjacency matrix for message propagation. What it does is basically it samples neighborhood. So it's a very algorithmic way of doing it. So it does it recursively. So what it does is, let's say you have the red node, uh, it will take the set or the subset of its neighborhood and aggregate the message from that subset of neighborhood to the red node, and then it will pass to the other uh, node. It won't at any point consider all the node features in one memory. So what I was talking about before, the feature matrix, which we use to define or do any kind of inference or learning, it won't take these feature matrices into account. It won't store that feature matrix. It will just traverse through each node at one point and then look at that node. What are the neighbors? Uh, Pass information from those neighbors and then move ahead. And it also introduced something which was very different, which was the aggregation. So till now in graph convolution network, it used only mean aggregator. So it used to just aggregate information from the neighbors, uh, do its average, and then uh, pass it to the target node. They introduced multiple aggregators, which include LSTM aggregator, pooling aggregator, which is max pooling, mean pooling. So basically what you do is out of all the neighbors, whichever has the maximum value of certain feature will be assigned, will be passed as an information to the target node, rather than combining the information from all the neighborhood. So you can do mean pooling, max pooling. There is an LSTM aggregator, which is a weighted mean pooling. This is in a very uh, roughly put, this graph stage is basically gives you more flexibility in terms of inductive learning and in terms of choosing your aggregations. The second is gated graph neural network. Uh, so the the downside of GCN and graphs is basically they can only be only be modeled till 2 to 3 layers. So they are only 2 to 3 layers deep uh, because they couldn't go beyond that. They used to be vanishing or exploding gradients. So this whole method came after, actually this came before them, but the the subsequent methods used more deeper graph neural networks, which could go beyond 10 layers. So you can do message passing for 10 subsequent times. So this gated graph neural networks so the whole concept of gated graph neural networks was to assign parameter and share them across layers, or to have a recurrent state update. So which is very common to what you do in recurrent neural networks. So you have a gated function where, and you pass that state rather than passing all the weights. The next one is Dnns with edge embeddings. So till now, whatever we talked about was only using node features. But what if you have features on the edges as well? So then you have different methods which combine both the node embeddings and edge embeddings, and then perform any kind of inference or and design a neural network. Just introducing it here so that you can know the breadth of what can be done. So in these kind of methods, what they do is they combine the node features, like the neighborhood features on the nodes. Go back to the same example, which is here. Yeah. So you combine the information from the neighborhoods, but you also combine the information from the edges of these neighborhoods. These edge, when I say edge features, it's basically like, okay, a user is a friend of another user, but what kind of friendship lies between them? So that will be stored in an edge feature. That this kind of there can be different kind of friendship or different kind of edges, and that can also be combined, and this is done using an edge embedding. So there's another kind of variant of DNNs which uses edge embeddings. And yeah, so these are some of the variants of graph neural networks. Roughly from here onwards, people have come up with more advanced and sophisticated graph neural networks, but they have all been originated from one of these architectures. Some of the applications that has been used very viciously in these days using graph neural networks has been in social networks, neuroscience, scene, and everywhere it's been used. One of them nowadays it's very common is using graph neural networks for scene understanding, where you basically want there is a scene of a, let's say, a horse riding of a person riding a horse, and then you want to perform some kind of a relational inference that is this horse also in any way connected with the car that is going past the horse, basically. So these kind of scene understandings are getting very popular, and the recommender systems is very obvious with graphs. Transportation networks, drug molecule drug molecule classification, which I showed you an example before using graph classification. And also the most common application is still in social networks, which is where I work on. And I'll basically give a very brief overview of what I have been working on, which is just like a 2-slide thing. So my research topic is basically something beyond graphs, which is hypergraphs, where instead of an edge connecting only 2 vertices, an edge can connect multiple vertices. I know it's a bit hard to grasp this thing, but you can understand this hypergraph as something like connection between 2 clusters. So what if there are not connection between 2 nodes, but there are connection between a cluster of nodes. So this is and then you can do also you can coin up with new theory or architecture based on these hypergraphs. One of them is to perform tag recommendation or image classification. If anyone is interested, this is one of the research topic that I am very much interested in, and I think I've passed the time. So thank you so much for listening to me, and if you have any questions, please let me know.
Thank you, Devanshu, for the nice presentation. Since your screen is blacked out, I presume you're still there, right?
Yes.
Okay. Yeah, thanks again for the nice presentation. I guess there might be questions from the students. So if you have questions, maybe just raise your hand uh, in the list, and I can invite one by one. Okay. So we have Chetan first. Chetan, go ahead.
Sir, I wanted to ask that why we use just adjacency matrix, because we can use adjacency list, and the model you showed that they use neighbors and neighbors for
Yes.
message passing. So the adjacency list seems to be more intuitive in this. So why not adjacency list?
What do you mean by adjacency list?
So it's a graphical, like it's a way to represent graph in which for each node we store its neighbors. So like for
Hmm.
A we store A B C D,
Oh,
for B we
yes,
store.
yes, yes. So basically a set of neighborhood nodes, and
Yes, yes.
that is what is used in graph sage, this one that I was talking about. So instead of using an adjacency matrix, it uses a set of neighbors, and then it performs message passing from only that set of neighbors. So at no point the entire adjacency matrix is in the memory, and
Okay.
that's how you perform inductive learning. So yeah.
Okay, I guess Chetan, that's clear to you. So do we
Yes,
have?
sir.
Okay. Do we have more questions? This is the time. I mean, if you have any questions related to graph neural networks or in general anything related to research on graph neural networks, go ahead. I mean, we have an expert here, so this is the right time. Okay, Anangsha.
Yes, sir. Good evening, sir. Sir, in link prediction in graph, the as a activation function ReLU was used. So, is that the standard way, or we can use other activation functions also?
Mm, Yes, you can use other activation functions as well. There have been a lot of other methods which are used or which have basically experimented with very different architectures. This is just for the sake of simplicity that I've shown the same architecture for all these different tasks. But
Okay.
yes, you can use different kind of. So these are all hyperparameters that you can come up with. But it's just for the sake of simplicity that I have created the same architecture for all these tasks.
Okay, sir. Yes, thank you, sir.
Okay, maybe Costo, you can go now.
Good morning, sir. Can you just briefly explain how graph neural networks are applied in meshes and graphics?
In
Meshes and graphics.
oh, so uh, in so one of the most common thing in meshes is to do some kind of clustering so that you know what kind of structure the mesh is inside the mesh are different from what kind of structure. So in meshes, one of the very most common strategies to perform this node clustering. So you assign nodes in a mesh, and then those nodes are clustered in a way that that can perform like can have strength, more strength, less strength, and have some kind of agility and all these things to that can add to the mesh. So these kind of things are very common in meshes. And I'm not very sure about the graphics, but mesh analysis can is very is how uh, this clustering is how is it is done in mesh analysis.
Thank you.
I hope that was clear to you, Costo. Or did you also
Yes,
mean
sir.
the meshes like finite
Yeah,
element mesh, those type of meshes?
that I am not very like proficient on the mesh part of those things like finite element methods, so I can't comment on that.
Maybe I can add to it. So if you have, for example, Costa, if you have a problem where you are doing transient simulation, so if there is an object which is changing in time, changing its shape in time, and you want to use graph neural networks for the mesh, what is done is these graphs, the concept of connecting nodes that is applied to, for example, if you have a certain node in the mesh, how that node is moving across in time, that is modeled through graph neural networks. There is a very nice paper also I can send afterwards to you on how graph neural networks are used for mesh simulations. Yeah.
Okay. Thank you.
Okay. Yeah. Any more questions? Okay, I guess we have no more questions. So I would just also like to add, I mean, this is really an interesting topic. And in case you are interested to work in future on graph neural networks, you can always reach out to Devanshu. You can reach out to me. I can always connect you guys with him. Yeah. So it's a nice topic. Try to read more if you want. If you want to know more about it, there's a lot of material online, and we are always available to discuss further. Yeah, I guess since we have no more questions also, this is the time to then close the session. I would again like to thank Devanshu for giving his time. I think he spoke for an hour, quite a lot of effort. So thanks, Devanshu.
Thank
Yeah,
you for
with this,
inviting.
yeah, I think it was a pleasure to have you here. So I guess we can now close this session. Bye bye, everyone.